Hello everyone, welcome back to this online class. Today we are going to look at the applications of first order ODEs of first degree. And in particular, we are going to look at the cooling of substances. Now, when you talk of cooling, it is a process that is governed by the Newton's law of cooling. Let us state it. The statement of the Newton's law of cooling, it states that the rate at which a substance cools is directly proportional to the excess temperature above the room temperature. It can be room or surrounding temperature. So let me write above the room stroke surrounding temperature. So this is the statement of Newton's law of cooling. Now, mathematically, how do we write it? You see, we are talking about temperature at time t. There's also room temperature, and there's also the rate at which that substance cools. So we are going to say that let me talk of T be the temperature of the substance at any time T. Let T naught this one, let it be the room temperature, room or surrounding temperature. Therefore, we are told the rate at which the substance cools, that is dT with respect to time, is proportional to the excess temperature above the room temperature, the excess temperature. So we subtract T minus T naught. If I remove the constant of proportionality, remember this is the statement of the Newton's law of cooling mathematically. So you can write here, this is mathematical statement. Mathematical statement of Newton's law of cooling. Now, how do we get rid of the proportionality symbol? We need to introduce a constant of proportionality so that this equation can as well be written as dt with respect to time is equals to a constant k times t minus t naught. So this is the ODE governing the cooling. This is ODE governing cooling of a substance. Which ODE is this one? It is linear. You can solve it as linear ODE. It is linear in the dependent variable t. That equation is also separable. So you could decide to solve as a linear ODE, use integrating factor method, or solve it as a separable ODE. You will still get the same answer. So let me again bracket this. And so every time you are told that a substance is cooling, then think of this ODE. That is the one that you need to solve. As long as you know the room temperature and some conditions given, you should be able to solve such type of a question. Now, let me give you maybe two examples. We start with example 1. So right here, example 1. We look at two examples. The first example is example 1. So in example 1, we are told that if a body in air at 25 degrees centigrade cools from 100 degrees centigrade to 75 degrees centigrade in 1 minute, find its temperature at the end of 3 minutes. So let's analyze this problem and then try to work it out. We have time t, of course, in minutes. This is in minutes. And we have temperature. T capital, that is in degrees centigrade. So we have those two columns. Now, initially the temperature was 100. Remember, the body is cooling from 100. That's the starting point. So we say T is equals to 100. That is the starting point. So that's when the time is equals to 0 minutes. When we are just starting. Now it cools to 75 degrees centigrade in how many minutes? Just 1 minute. So at the end of 1 minute, we are told the temperature is equals to 75 degrees centigrade. Now, what are we asked to determine? We are asked to find the temperature at the end of 3 minutes. At the end of 3 minutes, what will be the temperature? That is the question. So let me put a question mark. At the end of 3 minutes, we don't know the temperature. Now, but we know the ODE that you're supposed to solve. It is this one. This ODE, that's what you're solving. dt is equals to kt minus t naught. Now, what do you think is the room temperature? Look at 25. It is the surrounding temperature, the temperature of the air. This body that is cooling is surrounded by air. So room temperature is T naught is equals to 25 degrees centigrade. Now let's form the ODE. So our ODE for this problem is dt is equals to k, then we have t minus t naught, which is 25. And I told you here that the k, I already explained it, but let me just write. Take note is that the k here, k denotes a constant of proportionality. So that is constant of proportionality. So our ODE to be solved is this one, and I told you can solve it as a linear ODE or as a separable ODE. So for instance, let's solve this as a separable ODE. It's easier. When I separate the variables, I'm going to get dt over t minus 25 is equals to k dt. And you see we have the limits. When the time is 0, the temperature is, we are integrating. So you need to plug in the limits that when time is 0, the temperature is 100. That is this two. And also when time is 1 minute, the temperature is 75. So you integrate and you plug in the limits of integration. So what do we get on the left-hand side? When you integrate, we are going to get ln of t minus 25. And the limits are from 100 to 75. On the right-hand side, we are going to get k times t. Of course, don't write a constant of integration because we know the limits of integration. In this case, our limits of integration for time t is from 0 to 1. So what do we get? On the left-hand side, we are going to get ln of 75 minus 25, then subtract ln of 100 minus 25 is equals to k into 1 minus 0. So that this can also be written as 75 minus 25, that is 50. So this log of 50 minus log of 75 is equals to k. Or use the laws of logarithms on the left-hand side to divide those two. So you could say that k is equals to log of 50 over 75. And you see this can be simplified. This is the same as log of 2 over 3. When you divide by 25, because there are 2 times, the other one is 3 times. So that is the value of k. So I can just write it here that therefore, our constant of proportionality is ln of 2 over 3. Log of 2 over 3. So that is the constant of proportionality. Now, we still have some limits to apply. Let's see. Now, we already found the value of k. We still have another condition to use. This one, when time is 3, I don't know t. That's what we need to use. This and any of those 2 conditions. I could use the 3rd condition and the 1st condition. So the same integral. So you can write here similarly. The same integral is the integral of dt over t minus 25 is equals to k dt. Again, the integral. Now, initially, when time is 0, temperature is equals to 100. When time is 3, let's write here 3. What is the temperature? Let's use T capital, because that's what we need to predict. Already we know the value of K. So when you integrate this, we are going to get a natural log ln of T minus 25. And This is from 100 to t is equals to kt, and now the limit for time is from 0 to 3. So this implies that, let me substitute the upper limit, we'll have ln over t minus 25, then minus lower limit is ln of 100 minus 25 is equals to k into 3 minus 0. So this can be written as ln over t minus 25 minus ln of 75 is equals to, remember we know the value of k, let me replace, and also here we have 3, so it is 3 ln 2 over 3. I've replaced the value of k by log of 2 over 3. So I need to make t the subject in this equation. Look at the left-hand side. You can be able to combine these two logs. These can be combined into one log, and also use the laws of logarithms. This can be the power of 2 over 3. So on the left, you can say, or the log of t minus 25 divided by 75 is the same as the log of 2 over 3, and this is supposed to be raised to 3. Log of 2 over 3 cubed. I've used the laws of logarithms so that when I take exponential on both sides, those logs will disappear. So that we'll have now t minus 25 over 75 is the same as 2 over 3 cubed. And so from here, you can make t the subject. From here, it means that t is equals to 2 over 3 cubed times 75, then plus 25. This is times. So let's press this in our calculator. You can press, of course, 2 cubed is 8 and 3 cubed is 27. So it's like we have 8 times 75 divided by 27. The answer you get, you add to 25. And so that should give you 47.22, which is the same as 47 and 2 over 9. So this is equal to, let me write that as improper fraction, 425 over 9, 425 over 9 degrees centigrade, which you can also write as 47.22. The 2 is recurring. 22, that 2 is recurring, degrees centigrade. So that is the temperature when at the end of 3 minutes. And you see this substance continues to cool. So you could even determine the temperature at the end of 10 minutes. You could determine how long will it take for the temperature to be 0, etc. So that is example 1. Another example is this one, example 2. Again, still on cooling of a substance. So we are going to write the question in example 2. So in example number 2, we have this question. We are told that detectives discover a murdered victim at 6 a.m. and the body temperature of the victim is 25 degrees centigrade. In 30 minutes later, the police surgeon arrives and the body temperature of the victim is found to be 22 degrees centigrade. if the air temperature is 15 degrees centigrade and the normal body temperature is 37 degrees centigrade, at what time did the police surgeon estimate that the crime was committed? That's the question. Again, let's analyze this problem to make our work easier when solving it. So we write here solution. Now we have temperature. Let's start with the time t, and now time we are going to have it in minutes. Then we also have a column for temperature. T capital, that is in degrees centigrade. Now, what are we told? That look at the statement. This victim was discovered at 6 a.m. and the body temperature of the victim is 25 degrees centigrade. So you see, we don't know when the murder took place. So when time is equals to 0, we expect that the normal body temperature of the victim is 37 degrees centigrade. After 30 minutes, the police surgeon arrived. So when time is equals to 30, the temperature was found to be 22 degrees centigrade. And you need to write that. Now, we are told the air temperature is 15 and the normal body temperature is 37. At what time did the police surgeon estimate that the crime was committed? So, you can write here the surrounding temperature. That is T naught is equals to 15 degrees centigrade. There's something I've not used here. Look at 25. At 6 a.m., the temperature was 25. So we can say that is the T naught. Let me not, because we don't know the time when the temperature was 37. So I'm going to rub this and write here 25, because that's when we start measuring temperature. So this is 25 degrees centigrade. And remember, this is at 6 a.m. At 6 a.m. That is when the first temperature of the victim was taken and was found to be 25. Now, 30 minutes later, you again measure the temperature and it is found to be 22 degrees centigrade. I've written there. We are also told the room temperature to be 15. And we know the normal body temperature of a human being is 37. We want to know, when was the temperature equal to 37 degrees centigrade? So that's the question. If the temperature is 37, when was that time? T is equals to what? That is the question that you need to ask yourself. So now we can now solve it. The ODE governing the cooling of the body's temperature is this one. dt is equals to K into T minus 15. Room temperature is 15. So this ODE is separable. We can solve by separating the variables. This is separable ODE. So when you separate the variables, what are we going to get? So we collect the capital T's on one side and the small t's on the other side. So that, let me write it down here. When you separate the variables, we are going to get dt over t minus 15 is equals to k dt, the small t. So we are integrating both sides. Now look at the conditions. Let me take you here. That when time is 0, the temperature was 25. So I'll write it here that when time t is 0, the temperature T capital is 25. Another condition is when time is 30, the temperature is 22. So the other one I'll write here, 30 minutes, here it is 22. Remember, it is cooling. So integrate and plug in the limits of integration. That will help you find the value of k. So when you integrate this, you get the natural log of t minus 15. And the limits here are from 25 to 22. So from 25 to 22 is equals to, when you integrate the right-hand side, you get k times t. The limits are from 0 to 30. When you plug in the limits, you get this. Or let's start with the 22. So we'll have ln 22 minus 15 minus ln 25 minus 15. That's the left-hand side, is equals to k into 30 minus 0. Or this is the same as ln 22 minus 15, that is 7. So ln 7 minus ln, the other one is 10, is equals to 30k. So you could make k the subject. This can also be written as ln 7 over 10 is equals to 30k. You see, 7 over 10 is 0.7. So make k the subject. So this means that k is equals to 1 over 30 ln 7 over 10. So that's the value of k. Now we need to find the time t when the temperature was 37 degrees centigrade. So again, we go back to the ODE that we're integrating and plug in the first limits or the first conditions and the third conditions that we have in our table up there. So you can just write here similarly. Again, we have dt, t capital over t minus 15 is equals to k dt. Remember, we are integrating. Now, when the time is 0, the temperature was 25. I don't know the time when the temperature was 37. That's what you need to determine. So again, let's integrate. When you integrate this, you're going to get, so you can say this implies that ln of t minus 15, the limits are from 25 to 37, 25 to 37 is equals to the other one is k, and use red, kt. And now we know the value of k, and this one is from 0 to t, 0 to t. Let's plug in the limits of integration. So write or ln 37 minus 15, then subtract log of 25 minus 15 should give us the right hand side is just k into t minus 0, which is just t. And you know the value of k. Remember, we need to determine time t. So this can also be written as log, what is 37 minus 15? That should give us 22. So that's log of 22. 25 minus 15, that is 10. So this log of 10 is equals to kt. And I'll also replace the value of k. So or here we can now write log of 22 over 10 is equals to k, which we got 1 over 30. 1 over 30 log 7 over 10 times t. So let's make t the subject. So from here, this implies that now the t that we want is equals to ln, that is 22 over 10, which is 2.2, divided by 1 over 30 times log 0.7, that's 7 over 10. Let's press this. Log of 2.2, so you can press that in your calculator. So I'll start, remember ln, still the same log. So log 2.2, the answer you get, you divide by log 7. No, not 7, 0.7. Then I can see, again, divide by 1 over 30. That's the same as multiplying by 30. That should give you negative 66.32. Negative 66.32. I'll write it here. It is equals to negative 66. And it is 3173. 3173. Let me write that one. And you see, time is in minutes. So this is minutes. Somebody might ask, can time be negative? That is the question that you might be asking yourself. Remember, we are going back to when the crime started, when the temperature was 37. So it is backward. When it is the negative means you're going back. So let's go back to the table and predict at what time was that crime committed. So we'll come here, and now we know that when the temperature is 37, the time here is negative 66. So negative 66, when you go backwards to 6 a.m., we are going to subtract, because at 6 a.m. the temperature was 25. So backward of 6 a.m. at what time is that? So it is 6 a.m. then minus 66 minutes. So we don't know that time. So we'll write here you need 6 a.m. minus 66 point, it was 66.3173, 3173 minutes. What time is that? So 6 a.m. is in 24 hours. That is, you can convert to 24 in our clock system so that it makes our work easier when subtracting. So this is the same as 0, 0, 0, 0600 hours minus 66.3173. So you see 66 is almost 1 hour back and some 6 minutes. So that means it's the same as 5 a.m. minus 6.3173 minutes. So 6 minutes just before 5 a.m. that is 4 point what? 4.54 a.m. When you subtract, you get this. That is the 66.3173 minutes just before 6 a.m. So that means the time that the crime was committed is at 4.54 a.m. So we can now conclude here and say that can come here and write the time that the crime was. So you can say here that therefore the crime was committed at 4:54 a.m. I said it's just 66.3173 minutes before 6 a.m. That is the same as 66.3173 minutes before 6 a.m. You see, this victim was discovered at 6. So we wanted to know when was this crime committed. So this is all about anything to do with the cooling of a substance. Thank you all for watching this video. Please subscribe to my YouTube channel, that is Professor Francis Okech. When you go to the YouTube search, type Francis Okech or Prof. Francis Okech, and you will find me right there. Also, don't forget to comment, like, and share this video. When we meet next time, we look at more problems in applications of first order ODEs. Bye-bye.